Swayam Prabha. Digital India. Educated India.
Good morning. Today we will see another source of strength in structural materials, namely the atomic scale structures in solids. We have been saying that in structural materials it is all about strength, and so we need to investigate where the strength comes from. Now we have seen that the strength comes from interatomic bonding, the strength comes from the metallic bonds, particularly the ionic bonds in ceramic materials. Covalent bonds are usually responsible for strength in polymers, and we also noted that the ionic bonds are often not 100% ionic, they are partly ionic and partly covalent. So basically in many of these compounds you have mixed bonding taking place, leading to specific properties of the material in terms of strength, basically, right. So we are looking at strength, and the processing influences the structure influences the properties, and properties influence the performance. So I had given you an exercise to find out the interatomic spacing of two materials, and which of the two materials will have a higher melting point, and what is called as the Young's modulus. It is basically an elastic property. We had studied that in terms of the interpotential curve, the energy versus distance of separation curve, and we had seen that the total energy is given by energy of attraction and repulsion, and the corresponding force is the derivative of this energy curve at various points. So this is the energy curve, and the slope here is 0, and so is the force corresponding to the lowest point on the energy graph. So for this particular problem which has been given to you, I have plotted the interpotential curve for M1. Similarly, one can do it for M2 as well, and then here the equilibrium atomic spacing turns out to be 0.236 for M1 and 0.1651 for M2. So atoms are much closely spaced in M2 as compared to M1. And then if you look at the well, the energy well, so here the depth of the energy well is of the order of minus 5.32, and for M2 it is minus 13.7. Basically what you need to do is to differentiate the equation which is given here. So this energy equation has to be differentiated and equated to 0 to calculate the separation at 0 force, meaning the equilibrium interatomic separation. So this has to be differentiated and equated to 0 in order to get the equilibrium interatomic spacing, and then to get the depth of the energy well, you find out what is the En at that particular point, because wherever the force is 0, the depth is the maximum. So the depth of the energy well is maximum at force equal to 0. So having calculated this equilibrium atomic spacing, you use this value to get the depth of the energy well, which translates to a higher melting point where the depth is higher, meaning M2 having a greater depth of the energy well will have a greater melting point. And then the radius of curvature at this equilibrium position also defines the Young's modulus. So the Young's modulus in case of M2 again is higher compared to M1 because the radius of curvature is much smaller. The radius of curvature is much smaller as compared to the radius of curvature in M1. So you need to again differentiate this equation, this energy equation has to be differentiated again, and then you have the radius of curvature determined based on the first derivative and the second derivative, and then you get these two values for the M1 and M2 materials. So you can try this problem, which is very similar. So those who could not solve it on your own, you can take the previous solution as an example, and then try out your hand at this problem, where earlier R had a exponent of 1 because it was minus a by r. Now it is r raised to m and r raised to n, where m is not equal to 1, it is equal to 2. So there is a minor difference between the two problems, and therefore you can derive the expressions and calculate the interatomic distance. Now there is another issue, also find the force required to break the molecule, maximum force and critical separation at which the molecule breaks. So in this curve, this is the total force curve. So here the force is 0 at equilibrium separation, but then the force rises as the separation increases, and as the separation increases there is a maximum force, and at this maximum force, if the interatomic separation exceeds the maximum force, then you will have the breakage of the bond. So this interatomic separation at which the breakage of the interatomic bond would take place needs to be calculated, and this will depend upon where the maximum of the force will lie. So again you need to find out the maximum value of the force in the entire expression. I had also asked you in the previous lecture to find out the percentage ionicity of the bonds like CuAl2, nickel, and so many bonds were given, and you were to find out based on electronegativity of the elements involved. On the left hand side you see that the electronegativity of these elements is relatively small. On the right hand side you have, except for the inert gases, you have increasing electronegativity from boron to fluorine and from indium to tellurium and so on, and iodine. So you have these electronegativity, high electronegativity on the right and high electropositivity or low electronegativity on the left. So whenever you have a compound of an element which lies on the left with another element which lies on the right, it is going to have extremely high level of ionicity. Whereas if the elements lie, let's say both the elements are lying on the right hand side, for example boron nitride, boron and nitrogen, then they are not going to have too much of difference in electronegativity. So aluminum nitride, again silicon carbide, the differences are relatively small, and therefore the ionicity is going to be that much lower. And we have already seen that the degree of ionicity controls the strength as well as the melting point. So greater is the ionicity, the strength is more, and so is the melting point. So we do those calculations, and I have given you a number of values. I mean, if you are unable to calculate them, you have to just plug in the values in the formula that has been discussed in the last class, and then you can arrive at some of these values. The ionicity for carbon hydrogen bond, which is typical of polymers basically, has been put here as a reference because it's a purely covalent bond where the ionicity is 3.92%, and so is the case with CuAl2, which is present in an alloy of aluminum with copper. So you have a very small difference in electronegativities, 0.4 in both the cases, and therefore the corresponding ionicity is also very similar. So if there is a small difference in the electronegativity, then the degree of ionicity is going to be extremely small. That is what one has to remember. In contrast, you have potassium fluoride where the difference is of the order of 3.2, and therefore you have 92% ionicity. So it's practically 100%, very close to 100% ionic. So what we have seen is that processing affects the structure. So the structure is the one that is a source of strength. And today we are going to look at the atomic scale structures, how these atomic scale structures influence the properties and how these properties influence the performance. To give you an example, you have atomic scale structure of cubic boron nitride, which has got extremely high hardness, excellent, and it's therefore an excellent material for metal cutting tools. Whereas the same material in a hexagonal arrangement of atoms. So now here we are talking about atomic structure, meaning how these atoms are arranged with respect to each other. So earlier we were talking about interatomic bonding or interatomic strengths, and these are inherent to the atomic structure or the SPDF configuration of the atoms, even the ions. But here we are talking about structure, meaning arrangement of atoms, the arrangement of atoms in various ways. So here is a cubic arrangement of atoms. Boron nitride is the same compound, same ceramic with boron and nitrogen ions. You know that we have just calculated that the ionicity is relatively low because both these elements lie on the right hand side of the periodic table, and therefore the difference in the electronegativities is relatively small. And there is an extremely high hardness as a property because of its arrangement as cubic boron nitride. Had it been arranged as hexagonal boron nitride, the same boron nitride would have had very good lubricity and it would have been an excellent lubricant. What is a lubricant? A lubricant is a compound which has got very low shear strength. Now, if the shear strength is low, only then can you use it as a lubricant. You use oil as a lubricant, you use grease as a lubricant. Why? Because both these substances have very small shear strength. So if you put them in between between two surfaces, if you put these substances in between two surfaces, then they can be sheared very easily. The lubricant having a small shear strength enables easy sliding of one element over the other. Similarly, diamond has got extremely high hardness, so it's all carbon atoms but arranged in a different way, and it produces extremely high hardness. So diamond is typically used for wear resistant tool coating, so that the tools don't get worn out, tools don't experience wear and tear, tool life increases. Graphite on the other hand is again carbon atoms but arranged differently, which gives it softness and lubricity. We have graphite used in our pencils, right, with which we write, and that lead is very soft. So more is the graphite, softer is the lead, and therefore you have graphite pencils which are used for writing, and these are very soft, and graphite is used as a lubricant. So these arrangement of atoms are the sources of mechanical properties, sources of strength in the material. So that is what we are going to see in this lecture today. So the performance gets affected by the structure. As you see here, you have transparent, so the material is the same. The performance varies, the transparency varies depending on the degree of the kind of structure. The nature of processing changes the structure. So processing here and there is different, and therefore the three structures are different. So here you have translucent structure. So here this would be more or less amorphous, whereas here it is crystalline, and therefore you have complete opacity. So you have the same material with three different performances, three different sets of properties. Now if you look at the structural materials, we have already discussed different aspects of the strength, elasticity, plasticity. So what does it mean to us? So in case of metals, for example, if you were to take a piece like this, piece of metal, and pull it in uniaxial tension, so you are pulling this along this horizontal axis, then it will undergo a change in shape meaning it will elongate, and then elongation will never happen unlimitedly. It will not have it won't go on elongating forever. It will break at some point when there is what is called as necking, meaning there is a formation of a neck leading to a depletion of cross sectional area in a very small region, and then it will fail there. So when you apply a load, there is always a deflection. It can be detectable or it may not be detectable. So when I took the example of you pushing against the wall, irrespective of how hard you might push, yes, the wall is deflecting, but you are not able to detect the deflection. So what it means is that the force you apply is not enough to cause any detectable deformation in the wall. Plus, when you remove the force, the whatever deflection that you got after pushing is lost. So similar to a spring, when you push it, the load rises, and when the load rises, the deflection also rises, and up to a point it goes, and then when you release the load, the whole deflection becomes nullified. The whole deflection gets nullified. So the entire deflection becomes exactly 0 once the load is removed. So this part is called as elastic, but then I told you that there is a point beyond which there is permanent deformation that cannot be retrieved, that the material stays in its deformed condition. So there is a point Q beyond which the material does not recover its undeformed state. So what happens is that, let us say you have deformed it up to this point, then the material will stay in that deformed condition. So you have a certain extension which is called as plastic extension, meaning permanent extension, and this area, up to this point the deformation is uniform, meaning along the entire length of which is deforming, the change in shape is equally distributed. So the strain is equally distributed. So what we mean by strain is essentially extent of change in shape. We quantify the extent of change in shape. So earlier expressions were qualitative in nature, elasticity, plasticity, these were all qualitative in nature, but now we are talking about quantifying them. And so the resistance to deformation is essentially the force or the stress, and the stress per unit strain in the elastic regime is called as the Young's modulus. That is what we have been talking about in case of the interpotential curve. And then as you go on permanently deforming the material, this cross section continues to get depleted. Earlier the cross section was getting depleted very uniformly along the entire length, but when you at some point there is some strain concentration taking place, due to which the deformation gets concentrated in a small area, and then the material fails. And when the material fails, or when the cross sectional area starts getting depleted, the load carrying capacity of that cross section diminishes, and that is why the curve moves downwards. So you have these parameters, this quantitative metrics of strength. So you have yield strength, which is point Q, which marks the transition from elasticity to plasticity. Then you have the area under this curve representing the energy consumed by the material. So the elastic energy is consumed, force into displacement, which is essentially energy. So the energy under this curve, in the elastic regime, is the energy absorbed by the material during elastic deformation, and that is called as the resilience of the material. Similarly, there is some energy that is absorbed during plastic strain of the material. When the material gets permanently deformed, you have certain amount of energy that is absorbed, and that is called as toughness. So you have toughness on one hand and resilience on the other. So conceptually they are similar, but they are different in the sense resilience refers to the elastic region, whereas toughness refers to energy absorbed during permanent deformation or plastic deformation. So, naturally for talking about toughness, it is understood that you have crossed the yield point, you have crossed the point at which permanent deformation takes place. So, this way you are able to quantify the properties. Hardness is related with the again the yield strength, because hardness essentially is related with resistance to deformation. More is the resistance to deformation, more is the hardness. Something is harder to deform and therefore it has got more resistance to deformation. Now, we were talking about brittleness, etc. So, we come to that point over here. You have curve A, B and C of the same material. Material is the same. Let us say steel. Now, under one condition, under one structural arrangement of atoms, the load rises and what happens at this point A? It breaks into two. So, there is absolutely no permanent deformation, there is no yielding, there is no plastic deformation. So, here the material gets loaded up to point A elastically. So, if you release the load at any point before A, the entire strain is going to vanish, the entire extension is going to vanish. So, the whole deformation is going to be retrieved back. Now, this material is called as a brittle material. That is because there is absolutely no plastic deformation taking place. Whereas, material B again has got a different structure. So, it has got a very small amount of plastic strain that is possible. So, it has got extremely small toughness. So, again it will undergo not exactly brittle failure, but the features will be very close to brittle. Very small amount of energy will be absorbed in plastic deformation. That is because the extent of plastic deformation it will see is extremely small in nature. So, this is typical of another structural arrangement of atoms of the same material. So, now you see the difference in the structure in the force applied or force which can be withstood by the material, the strength of the material. So, at A it is relatively weak and it is brittle as well. In B it is stronger and slightly it has got slight amount of toughness, whereas in C the material is ductile and therefore it has got lesser strength because it undergoes plastic deformation much earlier, and the maximum strength also is much lower than what you see in case of B. So, B is the strongest, C is very ductile and very tough as well. So, A is brittle, maybe it is stronger than C, but then A does not absorb any energy during plastic deformation, whereas C does absorb plenty of energy in plastic deformation. So, one of the metrics of strength therefore is one is Young's modulus, which is the slope of this line, and then the tensile strength, which is the maximum strength that the material can put up to plastic deformation. Because what happens beyond the yield point is that the material starts so called work hardening, the material acquires strength during plastic deformation. So, one of the strengthening mechanisms is plastic deformation. We will see more about it in the subsequent lectures. I am just introducing to you the concept here, just trying to make an observation here that beyond the yield point during plastic deformation the strength of the material increases, and when the material strength increases there is some point at which it is maximum, because beyond that there is depletion of cross section to form a neck, and therefore the strength starts coming down and the material fails at point B onwards. So, at point B it just drastically drops down to 0 because there is no cross section left here. So, the metrics of strength include the tensile strength, the maximum strength, you have the yield point of the material, the yield strength of the material, and the so called ultimate tensile strength, which is given as the maximum load the material can possibly carry. So, you get instead of force you usually plot the force per unit cross sectional area, which is called as the stress. So basically the strengths, both yield strength and tensile strength, have the units of stress, load per unit area. So this is the procedure for calculating the yield point. So you have the Young's modulus, which is established, and then you take 0.1% of the gauge length, and then because what is the yield point? Yield point is the zone of transition from elastic to plastic. So how do you make it out? So you assume that, or you say that the material has just yielded. When the material has just undergone plastic deformation, that's the point at which it can be said to have yielded. So what is just undergoing plastic deformation? You have to define a strain. So 0.1% plastic strain is what has been defined, or 0.2% plastic strain is called as the strain at which you would say that the material has just about undergone yielding. So typical standard, which typical value of strain at which you take the stress is or so-called proof stress is 0.2%, and so 0.2% proof stress is taken as the yield point, and which is marked over here. So basically you take this force extension curve and convert it into a stress strain curve, and then you plot this. Of course, the nature of the curve will be the same, because stress will be force divided by constant, extension divided by constant, because the cross sectional area remains constant in case of elastic deformation. In elastic deformation, there is no change in the cross sectional area, and therefore the force is force divided by constant, and extension meaning delta L divided by constant is not going to change the nature of the curve as such, and therefore you get the proof strength, and the corresponding proof force is indicated over here. So we have seen that the sources of strength are related with the processing. So this is the process of making this particular part, and at various levels of length scales. At microstructural level, you go further, magnify it further, you magnify it even more, you go to increasing magnifications to atomic scale. You will find that the source of strength can be identified more and more exactly, more easily. So you have this process resulting in a certain structure of the material, which can be seen at different length scales. So this is the atomic scale structure of the material, and so we need to find out what introduces strength at atomic level, so that that gets carried forward at different length scales to the final macroscopic shape. So what we do is that now we will try to understand how the arrangement of atoms around each other results in an increase in the strength. So interatomic bonding is one thing, and atomic scale structuring is another source of strength, because that is what gives you the mechanical properties, and that properties give you the performance. So the source of strengths give you the so we saw in three graphs earlier the same material but different structures, different arrangement of atoms, and this different arrangement of atoms has led to different range of strengths in the material. So we have seen that its interatomic bonding is which is the metallic bonding that is responsible for the strength. We have seen the typical bonding energies for different kinds of bonds, and now we will see how the strength gets added to metals and alloys. We have seen this interpotential curve where you can infer about the mechanical properties of the material, and you see that between copper and iron, for example, the height of the interpotential well is much greater for iron as compared to copper, and therefore copper melts at about 1082 degrees centigrade, whereas iron melts at 1560 or something like that. So the well being deeper in case of iron, the melting point is higher than that of copper. Now, we will see how the arrangement of atoms as arrays, very regular arrangement of atoms as arrays helps in generating strength. We have seen that at equilibrium interatomic separation is decided by the interatomic forces of attraction and repulsion. And now if there is more than one atom, there are several atoms, let us say a number of atoms surrounding one single atom, then one atom will have bonds with several atoms surrounding it. That is why the crystal structures, which are essentially array of atoms around a given atom, result in an increase in strength, because now it becomes increasingly difficult to move a given atom out of position, because the other atoms have bonds with it, and then there is increasing difficulty in moving an atom out of position, meaning more force is needed to move an atom out of position. So most relevant crystal structures for metallic materials are face-centered cubic, body-centered cubic, and hexagonal close packed. Now, cubic structure means that you have atoms at each of these vertices, and then in face-centered cubic, you have an atom at the center of each plane. So if you look at the cube, each cube is made of 6 planes. So 1, 2, 3, 4, 5, and 6. So 6 planes are present, and at each plane you have a centrally located atom over here. So that is shown as a cut view here. So you have 1, 2, 3, 4 atoms in this plane, and then at the center of this plane you have one single atom which belongs to this plane. Whereas in case of body centered cubic, there is one atom inside the cell. So now you have this cube, 4 atoms at the top, 4 atoms at the bottom. So on 8 vertices you have 1 atom each, and then at the center you have 1 atom. So here you don't have anything at the center, here you have everything on the faces. All atoms are all the extra atoms are on the faces. That's why it is face centered. Here it is, nothing is on the face. The atom is at the center of the body, meaning center of the cube. So that's why it is called as body centered cubic. And then there is another structure which is hexagonal in nature. So you have 6 atoms at the top, 6 at the bottom. Then on the top face at the center you have 1, bottom face you have another one, and then there are 3 atoms which are inside this particular structure. You have these 3 atoms which are inside the cell. So all these atoms, similar to what we saw in the body centered cubic, are exclusively for this particular cell. So they are not shared by anybody. In face centered cubic, these face atoms, the atomic atoms at the center of every face is shared between 2 adjacent cubes or cells. So this cubic structure is also called as a unit cell, because you replicate this n number of times and you get a 3-dimensional structure out of it. So you can visualize this being replicated in all 3 directions, and then you get a 3-dimensional metallic structure of FCC nature. So similarly, you have an HCP structure, hexagonal close packed structure, where we have this 6 plus 1, 7 atoms at the top, 7 atoms at the bottom, and 3 in the central plane, which lies inside the cell. So this is a hexagonal cell, this is a body centered cubic cell, and this is a face centered cubic cell. Naturally, the properties, the strengths of these materials due to different crystal structures is going to be different, and so is the mechanical behavior under different conditions. For example, ductility, malleability, all such properties are going to differ from face centered cubic structure to body centered cubic to hexagonal close packed structures. So typically you have 7 crystal structure systems where you have the cubic, as we just saw. Here this is simple cubic, and then there are different versions of cubic like body centered, face centered, and so on. Then you have hexagonal. So you have A and B, that is these sides being equal, two sides being equal, but so all the sides of a hexagon are equal, but then the height is not equal to the side of the hexagon. So the C by A ratio, as it is called, the ratio between the height of the hexagon to the length of each individual side of the hexagon is given as typically 1.63, 1.58. So it depends on the material, and this C by A ratio is a very important parameter for a hexagonal close packed structure, and these structures therefore give different properties depending on the C by A ratio. So again, please remember that whatever you see on a macroscopic scale has roots in atomic scale structure. So unless something changes atomic scale level, we are not going to change at the macroscopic level, and conversely, if you want a macroscopic change, you need to make a change at atomic level itself. So you can either change the arrangement of atoms, or you can add different species of atoms, as in case of alloys, and you can add atoms so that they combine in the form of a compound. So there are a variety of ways in which you can alter the arrangement of atoms and their structures, but then the common point is that the structure determines the strength. So we have seen these structures in some detail now. Now we would like to see how many atoms belong to one particular cell, because we know that this atom is shared between two adjacent cells. This atom is shared by 8 neighboring cells, because you have 4 cells at the top and 4 on this at the same level. So you have 8 cells sharing this particular atom. So you have 3 types of atoms which are possible: corner atoms which are shared by 8 cells, atoms at the face which are shared by 2 neighboring cells, and atoms at the center which or inside the body which are shared by nobody. So you have the internal atom, atom at the face, and atom at the corners. So Ni in case of face centered cubic is 0, there is nothing inside. Then Nf by 2, the face centered, there are 6 faces and 1 atom per face. So 6 divided by 2 is therefore becomes 3 atoms, and you have 8 atoms at the corners, and each atom is shared by 8 faces and 8 cells. Each atom is shared by 8 cells, and therefore you have 1 atom per unit cell. So if you look at the simple cubic structure, there is nothing on the face, there is nothing inside, and therefore you have just 8 by 8 equal to 1. So in simple cubic structure, as in case of polonium, you will get just 1 atom per unit cell. Whereas in case of face centered cubic, in addition to the corner atoms, you have 6 faces and 1 atom per face. So you have 3 plus 1, 4 atoms per unit cell. For body centered cubic, you have an internal atom. There is nothing on the face, so Nf is 0, and then you have 8 corner atoms, which makes it 2 atoms per unit cell. And in hexagonal close packed structures, you have 3 atoms at the center, which are exclusively for this cell. So there are 3 interior atoms. Then you have 2 atoms on the face. Now this atom and that atom is shared by 2 adjacent hexagonal cells, and therefore the 2 atoms are shared by 2 cells each, and therefore you have 1 atom as a result of the atoms on the face. And then you have these 12 atoms. These are 12 atoms, 6 atoms at the top and 6 at the bottom, and these are shared by 6 cells which are around this, which surround this. So these atoms are shared by 6 cells, and therefore there are 2 atoms resulting from here. So now you have 6 atoms per unit cell for an hexagonal close packed structure. So you have for simple cubic 1, for body centered cubic 2, for face centered cubic 4, and hexagonal close packed 6 atoms per unit cell. Now, in common parlance, in technical language, both face centered and hexagonal close packed structures are called as closed packed structures, because they have relatively greater number of atoms per unit cell. There is another term called as coordination number, which tells you how many atoms are your nearest neighbors. So, for a given atom, how many atoms are the nearest neighbors for a given structure. So, as I said, greater is the number of atoms around, greater are the number of bonds, and therefore greater will be the strength. So, interatomic strength will get multiplied by those many times depending on the direction of the bonds and so on. But the point is that the number of atoms increasing leads to an increase in the strength of that structure. So, for metals, let us say for the body centered cubic material, this or structure, this central atom has got 8 atoms touching it. So, it has got 8 nearest neighbors. So, this coordination number is 8, whereas in case of a face centered cubic structure, you have the let us say you take this atom at the center of the face, you have 4 atoms here, okay, 4 atoms on the other side, and then 4 atoms. So, this face 1, 2, 3 and 4 atoms at the center of 4 adjacent faces will also be touching this atom. So, you have in all 12 near neighbor atoms for each face centered atom. So, basically you have the coordination number of 12 for the face centered cubic structure, whereas for body centered cubic it is just 8. Now, we will see how we quantify what is called as the atomic packing factor for different crystal structures. So, what it tells you is that atomic packing factor is the fraction of the solid sphere volume that occupies the entire cell. So, basically what it tells you is that how solidly is the unit cell packed with atoms. So, if the atomic packing factor is relatively less, then it means that there are more, it is less densely packed, whereas if the cell is more densely packed. So, close packed structures, for example, would be expected to have a higher atomic packing factor because the atoms are closely packed together. So, naturally the volume occupied by the atomic spheres will be a higher fraction of the cell volume as compared to the relatively less intensely packed structures of, let us say, simple cubic or body centered cubic. So, you have atomic packing factor of the different for different spheres. You have volume of spheres to volume of the total cell. Now, this depends on the structure, whether it is FCC, BCC or HCP, because the atomic packing factor, the total sphere volume, refers to the number of atoms per unit cell, right. It depends on the number of atoms per unit cell. So, the number of spheres, so the spherical volume will be given by the volume of one sphere into the number of atoms per unit cell. Now, you have examples of a few metals which have different where different structures are given here. Aluminum has got FCC structure, cadmium has got HCP, chromium body centered cubic. So, cadmium, cobalt and then titanium. So, these are all materials with hexagonal close packed structures, whereas many of the ductile materials, silver, nickel or aluminum, gold, so these are all face centered cubic materials, copper. So, face centered cubic materials have got extremely high ductility, they are easily deformable, they have malleability. So, we can make foils out of them. We know that aluminum is used for making foils, copper is used for making foils. So, more malleable is the material, easier it is to make foils out of it. So, basically what it means is that the structure is responsible for the kind of unique properties the material has. Body centered cubic, chromium, iron at room temperature particularly, tantalum, molybdenum. So, these are all body centered cubic. Tungsten is another body centered cubic material. And most of the high temperature materials, refractory alloys, are usually body centered cubic material. That is something that is noteworthy. So, now if we calculate the atomic packing factor, the first thing is we need to determine the volume of the cell. So, if you look at the FCC unit cell, then you have the so called lattice parameter, meaning the length of one side of the cube that is given by A. So, here you have A and A as the lengths of these two sides, and then the diagonal is given by radius plus 4 times radius plus the another radius. So, 6 times radius, radius 2 times radius. So, the whole distance is 4 times radius. R plus 2r plus r makes it 4r. So, given the Pythagoras theorem, you have a square plus a square equal to 4r bracket square, and therefore, A is related with the atomic radius as 2r root 2. So, you have been given atomic radius over here in nanometers. So, one can find out the size of the unit cell in terms of nanometers, in terms of the radius, atomic radius given in nanometers. So, if you look at the unit volume, unit cell volume, it is a cube, and therefore, this raised to 3 will, and therefore 16 r cube root 2. So, now you need to know the atomic packing factors, for which you have already found the cell volume, and then the total sphere volume is the volume of the sphere. So, we have 4 atoms per unit cell. In case of FCC, you have 4 atoms per unit cell. So, 4/3 pi r cube is the volume of one sphere, and for 4 spheres you have the 4 into 4/3 pi r cube. So, 16/3 pi r cube is the volume occupied by the spheres, which are exclusively for the one single cell of FCC. So, the corresponding atomic packing factor is the volume of spheres divided by the cell volume, which turns out to be 0.74. And it also can be shown, or it also turns out that the close packed structure HCP also shows an identical atomic packing factor, as opposed to a body centered cubic structure where you have an atomic packing factor of 0.68. Atomic packing factor of 0.68 is the is for BCC. Now, calculation of this A, that is the lattice parameter, is slightly tricky. Tricky means not as simple as in case of FC. There is a slight difference in the sense that the diagonal, which is the simple addition of the radii of these atoms, is not the face diagonal, but it's now the diagonal of the cube. So, this is the one end of the diagonal, and this is the other end of the diagonal. So, now you have this. So, this diagonal is the face diagonal. Okay. So, this is root 2 times A, right. So, A square plus 2A square, right, A square plus 2A square, 3A square equal to 16 into r square, because this is r plus 2r plus r. So, this is 4r. So, 3a square equal to 16r square, and therefore, a becomes equal to 4r upon root 3. And now, if you look at the total cell volume, it is a cube, and if you take 4/3 pi r cube into number of atoms per unit body centered cubic cell, it will be 2. So 2 into 4/3 pi r cube is the volume of the spheres divided by the total cell volume. Then you get the APF of 0.68. You can just verify it by doing it yourself. Now we come to the atomic packing factor of the hexagonal close packed material, hexagonal close packed structure. You have the length BC as A cos 30, that is A into root 3 by 2, right. BC is A, which is this is the length of A, which is essentially equal to 2r, and HCP cell can be visualized, or this hexagon can be visualized as being made up of 3 parallelograms put together, something like this. And so it is sufficient to find out the volume of this, or maybe area of this, and multiply by 3, and then take the height to give us the volume of the unit cell. So volume of the unit cell is 3 times 2r square c into root 3 upon 2. So that is because the area is 3 times CD into BC, CD into BC. So this is the BC is A root 3 by 2, and CD is equal to A. So 3A square root 3 by 2 is the area of the of this base. So now if you substitute for A as 2r, then and the total volume will be 6r square c into root 3. Now number of atoms per unit cell is 6, as we have just seen, and so total sphere volume is 6 into 4/3 pi r cube. Total cell volume is 6r square c root 3, and then you get atomic packing factor of 0.74. Well, we have assumed here as C by A as 1.63, and therefore we get that as 0.74. Similarly, you can compute the density also. So basically, based on the structural the nature of the structure of arrangement of atoms, you can compute the kind of density the material is going to have. For example, in case of face centered cubic, let's say you take copper for example, you have a face centered cubic structure. So number of atoms associated with each unit cell is 4 in nature, in number, right. Now rho is density, which is mass upon volume. So now per atom, what is the mass? It is the atomic weight of the that is weight of 1 gram mole of atom of material divided by the Avogadro number. So because 1 gram mole is the weight of Avogadro number of atoms. So let's say in case of copper, it is 63.5 grams per mole is the weight. Then 63.5 grams is the weight of Avogadro number of atoms. So per atom it is A by Na. Na is the Avogadro number. So you have one atom, the weight of or the mass of one atom into n number of atoms per unit cell. So in this case it is 4. So now we have got the mass of 4 atoms belonging to one unit cell divided by the volume of the cell. So basically you are getting the mass of the cell divided by the volume of the cell as the density of the material, because now these cells are going to be replicated uniformly in all 3 directions. So there is no reason why there should be any change in density. So the density computed based on one cell applies to a macroscopic chunk of material as well. So you get 8.89 gram per cc after substituting these values. So you have the n, so 4 into 63.5 divided by the volume of the cell we have calculated into the Avogadro number, and that is 8.89 gram per cc, and that is extremely close to the measured density of 8.94 grams per cc. So, this way it is possible to calculate the density or compute the density based on a single cell. So, I would leave it to you as an exercise to do the same thing for iron, which is body centered cubic, that is N equal to 2. The atomic weight is 55.85 gram per mole. So, instead of 63.5, it will be 55.85. Instead of 4 atoms per unit cell, it will be 2 atoms per unit cell, and then this volume will be different. Avogadro number is the same, of course, and so at the end of the day you will get the answer of about 7.88 gram per cc as the computed density of iron. So, we have different crystal structures which are possible. The material is the same, and therefore, the crystal structure can change. We have already seen how the 3 different properties for the same material can be obtained based on different structures. So, now if you heat the material, for example, right, then the crystal structure can change from, say, body centered cubic to face centered cubic, and then the properties also change very significantly. So, this is called as polymorphism. This is called as polymorphism because there is a possibility of getting different crystal structures by subjecting the material to the different conditions of temperature, pressure, and so on. For instance, carbon occurs as graphite, but it can occur as diamond under very high pressures and temperatures. So, basically it is polymorphism that is responsible for our ability to change or tweak the so-called microstructure and get different kinds of strengths, the different kind of mechanical behavior that we want from the same material. So, we can generate a range of strengths in the same material, and that is an advantage, and we will see how to do it later. But then the polymorphism is a very important property of these metallic materials, in that you can by changing the structure get a wide range of properties, mechanical properties in the material. So, you have in case of cubic structures, the parameters which can be changed are ABC, the lattice parameter, and the angles. So, depending on this you will get, for example, you have body centered tetragonal structure where A is equal to B, but it is not equal to C. So, all angles alpha, beta, gamma are 90, but A and B are equal, C is much greater than A and B. So, this is called as a tetragonal structure, and that gives you a great deal of hardness in the material as compared to when all 3 are equal. So, there are different structures which can be created from the same material and made to behave in a different way to give different strengths. An example of allotropic transformation of tin which led to a very funny situation was that white to grey tin transition produced some dramatic results in Russia. The winter that year was particularly cold, and record low temperatures persisted for long periods of time. So, the buttons which the Russian soldiers had on their uniform were made of tin, and they got exposed to this extreme cold conditions, due to which the crystal structure changed. So, body centered tetragonal structure at room temperature to a cubic diamond cubic structure under cold conditions, due to which the buttons crumbled, because now earlier they had strength to hold on, but they lost the strength due to cooling under extreme cold conditions. And so, this was called as a tin disease. And so, similarly, many of the organ pipes in churches also would crumble, because the tin would get transformed from body centered tetragonal at room temperature to a diamond cubic crystal structure which was in the form of a powder. So, you would find the organ pipes being converted to powder all of a sudden due to the presence of extreme cold. So if the temperature fell below 13.2 degrees centigrade or even through sub-zero temperatures, this would result in this conversion from body-centered tetragonal to diamond cubic structure. And so this was accompanied by a 27% increase in volume, and so the density from here decreased to the density of diamond cubic structure, which is much lower, and this volume expansion caused the disintegration of the so the volumetric strain, the volumetric deformation that took place, the expansion in volume that took place resulted in too much of strain which the material was not able to bear, and therefore this structure broke apart. There was too much of interatomic separation as a result of this expansion, right, volume expansion taking place, and then the bonds broke and the whole structure disintegrated into a powder. So this was about metals. We come to ceramics, which are again ionically bonded. So electronegativity is what we were talked about here. And then in case of ceramics, the cation and anion are linked with each other using inter-ionic forces. So the stable and unstable arrangements depend on the relative radii of the cation and anion. So this is a cation at the center, anions at all around, and since they are in contact with each other, I mean the central cation is in contact with all four, it is stable. Here also it is stable, but here the cation is too small, and therefore it is not possible for it to contact. So this kind of arrangement is unstable. So the structure depends upon the ionic radius. So if you look at the ionic radius of cation to anion, if it is very small, then only two atoms. So this is the arrangement that is possible. Intermediate, you can have three. As the radius of cation continues to increase relative to the anion, then you can approach the structures which are similar to those of metals. So if you have something which is close to or equal to 1, then you can have similar arrangements as atoms, but otherwise you cannot have stable structures where a cation is too small. Similarly, density of ceramics can be computed based on the two densities, linear addition of two densities. So Avogadro number of sum of atomic weights of all cations, atomic weights of all anions. And so what is meant by formula unit? So if you have, let's say, two cations, let's say Al2O3, so then you have the atomic weight of aluminum into 2 and atomic weight of oxygen into 3 divided by Vc into Na. So the formula remains essentially the same, and therefore we have for, let's say, barium titanate, basically based on formula, you have 1 barium ion, 1 titanium ion and 3 oxygen ions. So we have the total AA, that is atomic weight for one material as 35.545 gram per mole, and for other one is 23 gram per mole. So if you look at NaCl, sodium chloride, you have 23 for sodium and 35.45 gram per mole for chlorine. So based on this, you calculate the magnitude of so interatomic separation is given by the ionic radii 0.102 and 0.181, and the corresponding volume is therefore given to be that, and therefore the density of sodium chloride as computed from the unit cell is 2.14, whereas the measured value is 2.16 gram per cc. So again, these are structural configurations which we have already discussed, and then so one can calculate the minimum RC by RA for coordination number of 3. We know that coordination number refers to the minimum to the nearest neighbor atoms, number of nearest neighboring atoms. So you have a cation at the center, and then so the number of anions will give you the coordination number. So, these anions in contact with the cation. So, you have for a given RC by RA with a coordination number of 3 would result in this type of arrangement, basically an equilateral triangular structure. And so, purely based on geometry, one can calculate the RC by RA ratio as 0.155 for the coordination number of 3. So, based on this you have these ranges which have been set. So, less than 0.155 you have this, between 0.155 to 0.225. So, this just breaks down at 0.225, and therefore, you have this range up to 0.225. So, 0.225 onwards you have this type of configuration. So, you have these ranges, and similarly you have these arrangements of ions in case of NaCl, cesium chloride, zinc sulfide, and each of these arrangements result in different properties of the material. We have given some examples of different crystal structures with regard to ceramics, and you have different kinds of different numbers of cations and anions, where you have some symbol cubic, FCC, and so to summarize, in all, the addition of whatever we add to the material as in the form of chemical composition determines the strength of the metal or alloy. Either the alloying element dissolves in the parent metal without altering the structure, and or forms a compound with it. So, basically the structure of the material is responsible for the strength that we observe, and these. So, now we have seen two sources of strength: the bond strength and the strength due to structural arrangement of atoms relative to each other, due to which the strength due to bonds gets enhanced further, and we see an enhancement of strength due to different kinds of structures that we have seen. Thank you.